So today we're going to be looking at the mean value theorem, the MVT. So before we get into the mathematics behind it, let's just put it into something that's probably a little more familiar to us. So let's read this statement. If you were driving with an average speed of 45 miles per hour, would you agree with me that that means at some point you were driving faster than 45 miles per hour and at some point you were driving slower than 45 miles per hour? Unless that is, you were driving exactly 45 miles per hour the entire time. But if that's the case, then we're talking about a linear graph, and that's okay, just there's no calculus needed there. So again, from when you turn your car on and you start to drive, you're at 0 miles per hour until you park your car again and you're at 0 miles per hour. If you were driving at an average speed of 45, then that means you had to have been going a little bit faster and a little bit slower than 45 at different times, okay? Well, what the mean value theorem says is that you must have been driving exactly 45 miles per hour at least once. I'm going to write that down. If your average speed equals 45 miles per hour, then you must have been driving exactly 45 miles per hour at least one point in time. That's, in a nutshell, what the mean value theorem is saying, okay? Let's look at that graphically. And I'm going to now start to switch from talking about speed to velocity, okay? So here's a position function. Notice on the y-axis we've got our position in miles. On the x-axis we've got our time in hours. We started at a position of 0, we went up, we went back down, we went up, we ended at a position of 90, okay? If I find the average velocity, we have a formula for that. The average velocity is the change in position over the change in time. Well, my time is going from 0 to 2. Oh geez, 2 minus 0, sorry. My position at 2 is 90. My position at 0 is 0. So I have 90 minus 0 all over 2 minus 0, which is 45 miles in my numerator, hours in my denominator. There's my 45 miles per hour. When we find the average velocity, by the way, we are finding the slope between the endpoints, right? That's that average rate of change. So I'm just going to go ahead and draw that in. No, I didn't miss horribly. There, that's my 45 miles per hour. That's the slope of that red line. The mean value theorem said your instantaneous rate of change will be 45 at least once. Well, remember, instantaneous rate of change is slope at a single point. So let's think about where on this graph I would have a tangent line that also has this slope. So almost think like, let me grab my Post-it note. Oh, where is it? There it is. And of course it's sticky. So let's take this Post-it. Let's keep that slope the same and let's just slide it up. I know you can't see it, but it looks like I hit right here. So it looks like at that point, I have the same slope. Sorry, I didn't mean to move the page. Let's keep sliding it. I'm trying to keep it the same slope. It looks like that's going to happen again here. It looks like right here. I also see how all of these are parallel to that red line? Could also slide it backwards, couldn't I? It looks like when I get to this point here, so the idea is our exact or our instantaneous speed will be the same as our average speed. Okay, I'm going to write that down a couple of different ways. This is kind of what I was just saying, is that the average rate of change is equal to the instantaneous rate of change. That happens at least once. For us, it happened 3 times. We could also think of it as, let's change colors so we can see that. The slope of the secant line, remember the secant line means between 2 points, will equal the slope of the tangent line, right? So my red is my secant line, my dashed lines are my tangent lines, so they have the same slopes. We could also say, I kind of already said this is kind of like maybe a stepping stone. The slope between the endpoints equals the slope at a single point or at one point. That's really the same thing. I really just defined what it means to be a secant line. It's a line that connects 2 points. A tangent line is a line at 1 point. Okay, so this is essentially what the mean value theorem is saying. Okay, that at some point, we had 3 of them. I'm going to call that like t sub 1, I'll call that t sub 2, and I'll call that t sub 3. At these 3 points in time, we were driving exactly 45 miles per hour. Okay, let's write this down in terms of mathematical definition. The mean value theorem has 2 conditions for it to work. Number 1, your function must be continuous on the closed interval, and your function must be differentiable in the open interval, meaning we don't talk about differentiability at an endpoint, do we? If these 2 things are true, then there exists at least one number c in the interval a to b. If c is in the interval a to b, that means c is an x-coordinate. So there's at least one point in time, or one x value, between a and b, just kind of pointing that out, such that f prime of c, the slope at that point, will equal the slope between the endpoints. I'm going to write that down. This side represents the slope of the tangent line at x equals c, whereas this side represents the slope of the secant line that connects A and B. I know I'm writing the same thing over and over and over again. I'm just rephrasing it. Okay. But we're essentially saying if your graph is continuous and if it's differentiable, there will be a point, at least one point in time, where the derivative is equal to the slope between the endpoints. That's all we're saying. Okay. Pause if you need to. We're going to slide over here and see how this works. It says find the value for c that satisfies this mean value theorem for this function on the closed interval -1 to 1. First of all, if we want to use the mean value theorem, we need to check, is my graph continuous? Well, it's a cubic. Yes, it sure is. Is it differentiable? I guess I could have abbreviated that. Well, again, it's a cubic. There are no corners. There are no cusps. So both of those things are true. So here's what we're going to do. Here's my A and here's my B. So let's start by writing f prime of c is equal to f of 1 minus f of -1 all over 1 minus -1. I'm going to go ahead and just keep cleaning up the right-hand side. Right? This is like my f of x. If I plug in a 1, I get a 1 minus a 1 minus 2. If I plug in a -1, let's see, I get -1 minus 1. That's a 0. On the bottom, I get a 2. So on the right side, I have a -1. On the left side, it says f prime of c. Well, let's first start by finding f prime of x. f prime of x is equal to 3x squared minus 2x minus 2. Well, if I want to find f prime of c, that just means let's change all of our x's into c's. Let's go fill that in here. So I have 3c squared minus 2c minus 2. So I have the derivative on the left equals, and this is the slope of the endpoints. They're asking us to find c, solve for c. Oh, well, it's just a quadratic. So if I add the 1, let's see if this factors. Looks like it's going to do 1, 1. Perfect. So I get c is equal to negative 1/3. C is equal to positive 1. And it's okay that we got 2 answers, because look at the graph above. Remember how there were 3 points in time where that happened? So we said at least once. Well, we found twice, but be careful. Be careful. They're saying back here there exists at least one number c in the open interval, which means we do not include the endpoints as potential answers. So if my interval went from -1 to 1, I'm not going to include c equals 1. So our only value for c that satisfies the mean value theorem is -1/3. Okay. All right, let's take a look at the next page. Same directions. Find the value of c that satisfies the mean value theorem for this function. So again, we want to check, is our graph continuous? Well, graph of 1 over x between -2 and 3? No. Oh, hey, great news. We're done, right? If the graph doesn't even meet the first condition, then we can't find a c. So we'll say the mean value theorem does not apply. That's good news. That saves us a lot of time, because f of x is not continuous at x equals 0, which is in our interval. Then we're done. That's just it. It doesn't work. Okay. So that's the mean value theorem, and I know it doesn't seem like a really big deal. It doesn't seem like a big deal at all. And at first, you're right, it doesn't. The bigger deal, which is going to be really hidden for us, is that the mean value theorem is most often used to prove other theorems for us. So it's kind of a stepping stone to get to other things. Not that we're proving anything, I don't want to freak you out. Right? But that's really how the mean value theorem kind of connects to what we were doing yesterday. We have the mean value theorem corollary number 1. A corollary is like a theorem that comes from another theorem. Okay, it's like a stem off of. So the mean value theorem corollary number 1 says if, and we're not going to do any proofs, but if f prime of x is greater than 0, then f of x is increasing. That should sound extremely familiar because we've used it. Back in Unit 2, we used it a lot. Likewise, if f prime of x is less than 0 or negative, then f of x is decreasing on that interval. Okay, so again, it's not new information for us. We use this with particle motion. We talked about it with sketching derivative graphs, but it will prove to be extremely useful for us when we're finding extrema, maxes and mins. What we are going to do in order to determine when a graph is positive or negative, we're going to use a sign chart, and we've been doing sign charts. We did them in Algebra 2, we did them in pre-calc, we did them in some of our homework. And we're going to call this sign chart our first derivative test. We're going to use it to organize a lot of information. Okay? All right, so here we go. It says for this function g of x, we're going to state the intervals of increase and decrease and the coordinates of all extrema. All right, so this is what's tying us into yesterday. So the first thing I notice is we don't have an interval, so we do not have any endpoints. I'm going to just jot that down. No endpoints because the domain is all real numbers, which means we just need to find those critical points. Critical points are coming from the derivative. So g prime of x equals 4x cubed minus 16x. We're going to ask those two questions. When does the derivative equal 0? And where does it not exist? Well, guess what? It's a cubic. It exists everywhere, so we don't have to worry about that. I'm just going to keep on factoring. And some of you might say, I don't need to factor that all the way. I just know it's plus or minus 2. And that's fine. You're right. But you're going to find having this in factored form is going to make our sign chart much easier to make. So here we go. My critical points are at x equals 0, x equals negative 2, x equals positive 2. Okay? These are my possible extrema. What I'm going to do is I'm going to solve or determine when this graph is positive, when this graph is negative. So I'm going to come over here, I'm going to make a sign chart. Now I'm going to label it as f prime of x for two reasons. Number one, because it's going to help me determine that it's called g prime. That doesn't help. If this was g, this is g prime. It's going to help me remember that I'm going to go back to the derivative to plug things in. It's also going to help us in a few days when we start having what we call a second derivative test. So it's just a number line, right? So numbers have to go in order. There's my critical points. This is where the derivative is equal to 0. Well, now let's go in and see what's happening on either side. So if I plug in a negative 3 into the derivative, if this is the first derivative test, I want to know, is the first derivative positive or negative? So I'm going to be using this version right here. If I plug in a negative 3, this is negative, this is negative, this is negative, and a negative times a negative times a negative is a negative. Then I'm going to pick a negative 1 somewhere between here. This will be negative, this will be positive, this will be negative. The two negatives multiply into be a positive. If I plug in a positive 1, I get a positive times a negative. And if I plug in a 3, we get positives all the way across. So what this is telling me, when my derivative is negative, my graph is decreasing. When it's positive, we're increasing. Negative means decreasing. Positive means increasing. So just very lightly with my pencil I went in. So they're asking us to state the intervals of increase and decrease. So my graph is increasing from negative 2 to 0, then again from 2 to infinity. My graph is decreasing from negative infinity to negative 2, and then again from 0 to 2. So I did the intervals of increase and decrease. And now we want to talk about extrema. Extrema meaning maxes and mins. Well, look at this. My graph is going down, then up, then down, then up. Isn't this a minimum? Isn't this a minimum? So I have a minimum at negative 2 comma something and at positive 2 comma something. Looks like I have a relative max. I'll talk more about relative in just a second when x equals 0. This is an x to the 4th graph. We said the domain is negative infinity to infinity. So I know this graph is going up forever on both sides, which means this can't be the highest point because my graph will continue to go up. One of these will be the absolute min. I just don't know which one yet until I go find those y values. Okay. So these are coordinates on the graph. How do I find y values? I'm going to plug into the original function, to find points, right? These are y values, so we should go back to where it says y equals. So it's easy to plug in the 0. When we plug in the 0, we get a 10, don't we? Then I want to plug in a -2 and a +2. And the good news is, because those are even exponents, we're going to get the same answer for both. Shouldn't matter. When I plug in, actually, you know what? Let's make it a little easier on ourselves. Let's factor out an x squared out of those first two. I think that'll keep our exponents smaller. If I plug in a 2, this becomes a -4. -4 times 4 is -16, plus 10 is -6. And I get that for both because they had even exponents, right? Which means this is my absolute min, because this is the lowest the graph will get. This is just a relative max because the graph goes up forever. Okay? This is how we're just kind of tying it all in. All right, let's take a look at the last one. Same directions, new function. So the first thing again is we don't have any endpoints, right? There's no interval. When we think about the domain, the graph doesn't exist at -3. In fact, I mean, there's a vertical asymptote at -3 because we can't get rid of it. Something to think about. Okay, so we need to find critical points. Well, critical points come from the derivative. Maybe the first thing we'll do is rewrite this with negative exponents. So now I can say f prime of x equals -4 times x plus 3 to the -3rd. Chain rule says multiply by 1. I'm not going to write that down. And I'm going to go ahead and put this back and call it -4 all over x plus 3 cubed. That's my first derivative. And I would like to ask two questions. When does this derivative equal 0? And where does this derivative not exist? Right? Well, does this fraction ever equal 0? No. Never equals 0. But where does it not exist? Well, there's a problem in the denominator at -3. You know what? That does not surprise me. We had a problem at -3 from the beginning, so it doesn't surprise me that it's still a problem. It's technically not considered a critical point because it's not in the domain, but we're still going to put it on our sign chart. Right? The only important number, it's technically not a critical point, but the only possible place where we could have something going on is at -3. It's a discontinuity. In fact, I'm actually going to even kind of draw that in. There's a vertical asymptote there, so I want to remember that there's nothing there. So again, I can still plug in on either side. Let's pick a -4. Where am I plugging into? F prime. If I plug in a -4, this gives me a negative. Cubing a negative is a negative, and a negative divided by a negative is a positive. If I plug in something over here like a 0, well, this is positive. Positive cubed is still positive, and a negative divided by a positive is a negative. What does this tell me? This tells me that my graph is increasing from -infinity to -3, right? My derivative is positive. It is decreasing from -3 to infinity. It might be tempting to say we're going from increasing to decreasing, so it might be tempting to say that there's a maximum at -3, but remember, nothing is at -3. Right, so we're going to say there's no max, there's no min. By the way, we could have graphed this, I believe, from the get-go and not used any calculus at all. To me, this is the parent graph of 1 over x squared, which looks like that. It's been moved to the left 3 and a little bit of a vertical stretch. Right? This graph has no max, no min. It is increasing and then decreasing. Okay. So again, I mean, if that's something we knew what it looked like from the beginning, we certainly didn't need to do all of this, but I like showing you how it ties in.